I see some of you are still working and some of you are done. So let's just take a look and see how you did so far at least. Start out with a division problem. Walk me through it. Where would I start? Perfect. 34 doesn't go into 9, so we're going to see 34 into 90. And how many times? 2 times. Now, since we used the 0 as the last digit we used, we're putting the 2 above the 0. Then what?
Then take 2 times 34 would be 68.
Perfect.
68 minus
Perfect. 34 times 2 is 68, so we're going to take 68 away from 90.
and that will be 22.
10 and 8, so yes, that'll be 2 and 2, you got it. Then what?
Carry down your 9.
Bring down the 9, okay?
Then figure out how many times 34 goes into that number, and that would be 6 times.
So 34 into 229, you're saying 6 times, okay? And then?
And that would give you 204.
So 34 times 6, you're saying is 204. And then?
And that leaves with 25 left over.
So 25 is left over.
So then you carry down your 1.
Bring down the 1.
So then you figure out how many times 34 will go into 251.
Okay.
7 times, which is 238.
So you're saying 34 goes into 251 7 times. So 34 times 7 is 238.
That leaves your remainder of 13 and bring down to 6.
Okay, we bring down the 6.
And then 34 into 136 goes 4 times, which is exactly 136. So then it's 0.
Okay, so we put 4 above the 6 because that's the last digit we used. 34 times 4 is 136, so we're done. So 90,916 divided by 34 is 2,674. Show of hands, how many of you had that? Okay. How many of you are well on your way to it, just didn't get done yet? Okay. Anybody has no idea how to get there? Okay, that's good at least. Like I said, I will always allow you to use the calculator, but it's just nice to see if you can do it by hand. I'm an engineer by trade. I worked on construction sites for a long time. As I mentioned, it's not uncommon for me to show up and have my calculator damaged and not working and have to do something by hand. The second one, where would we start there? 6 times 4 is? So, leave the 4, carry the 2. 6 times 8 is 48. Plus 2 is 50. So leave the 0. Carry the 5. And then? Okay, 6 times 3 is 18. Plus the 5 we carried is 23. So 3 and carry over the 2. And then? Before we do the 2 times 4, what do we have to do? Put our 0. Perfect. And then 2 times 4 is 8. 2 times 8 is 16. Do we have to worry about this too? No. Usually when I move over, I put a line up there just so I know that anything I carry new goes above the line. So 2 times 8 is 16. So 6 carry the 1. 2 times 3 is 6 plus 1 is 7. And then? Okay, we total it up. 4 and 0 is 4. 0 and 8 is 8. 3 and 6 is 9. 2 and 7 is 9. 9,984. How many of you had that? Good deal. How many of you like multiplication way more than you like division? Okay. I don't disagree with you. As I mentioned last time, long division is the one operation I really try to avoid doing by hand if I can as well. Okay, well, with that said, for tonight's class, our first step, we're going to continue on with our operations with numbers. And we're going to look at some of our other operations, and we're going to look at combining operations. But first, I want to take a look at what does it really mean to do some of these operations. And I'm going to look at kind of the amount of the number now rather than the place values. rather than the names. Last time we talked about the count and the name. Then we talked about the place values as being the names of our larger numbers. But let's concentrate on the count for a minute here. What does it mean to have a count of 6? Well, like so many things in math, it refers to the number line. We mentioned this a little bit last time. We used the number line to define the less than and greater than symbols and some other things. Well, the number 6 is represented on the number line by something called a vector. And a vector is nothing more than a really fancy word for an arrow. What a vector is it's an arrow that starts at 0 and goes to that number. So 6 starts at 0 and goes to 6. Now, to perform an operation in math, we're dealing with those vectors. The operation of addition, let's say we have 6 plus 4. It's telling us to take the vector for 6, which we already have, and the vector for 4, which I'll put on here, like that. And it's telling us to combine them. So to combine them, I just put them end to end, or head to tail, sometimes called. Like that. Well, 6 plus 4 is 10, because this vector here ends up going from 0 to 10 when I put the two of them together. Make sense? Multiplication, when we define it as a vector, we mentioned last class 5 times 3 that multiplication is defined to be repeated addition. So when I take multiplication, that 5 times 3, what it's telling me to do got to come up with a faster way to draw out my number lines. What it's telling me to do is to take the vector for 5, like that, and copy it over 3 times. So 1, 2, and 3. So 3 times 5 ends up being 5 plus 5 plus 5, or 15. That's exactly where that vocabulary comes from, by the way. This is 5 3 times. The vector for 5 3 times. And we're used to working with those types of numbers, those positive numbers. Where the need to define the operations like this comes is when we start dealing with numbers that are not all on the positive side of the number line. For example, -6. Well, -6 is defined just like +6. It's a vector that starts at 0 and goes to -6. +6 starts at 0 and goes to +6. Now, if I had drawn this to scale, if I did a good job, these vectors, you should notice, are the exact same length. They have the same magnitude. They just point in different directions. So our numbers, the vectors that represent these numbers, have 2 important features. Their length, which we refer to as magnitude, and of course their direction. So if I go to do operations with one of these vectors, or with any integers, by the way, this is called an integer when it's a negative number. If I do an operation with integers like -6 plus 4, I can combine those vectors. Here's -6. I already have that in the blue one. +4 looks like that. If I combine them, if I drew them to scale, I can see really quickly that I end up at -2. Now, I don't expect that it'd be a real pain to draw out a number line every time we add these negative numbers. So I don't necessarily have to do it out to that detail, but I am thinking of this picture when I'm working with negative numbers. If I have something like So 17 plus a negative 9. Now in this case, this parentheses is not telling us to do anything first. It's just isolating that negative number so we know it's a negative 9 and not minus 9. When I'm doing a problem like that, I am thinking about that number line. I'm imagining a 0 point, and I'm doing the 17. 17 is a positive number, so it goes in the positive direction. Then look at the negative 9. Well, we said there's two components to a vector, magnitude and direction, length and direction. The negative 9 goes in the opposite direction because it's negative. Is it longer or shorter? It's shorter. So if I have its length and its direction, I don't even have to have them perfect. I just have to have them approximate here. This picture tells me two things. One, it tells me that my answer ends up on the positive side of 0, so that my answer is positive. Two, since my vectors point in opposite directions, it tells me that they work against each other, or they cancel out. In other words, it's the difference between their lengths. What's the difference between 17 and 9? It's 8. So the answer here is a positive 8. If I have a negative 12 plus 19, same thing. I have a 0 point. Which way does the negative 12 go? Negative, to the left. 19, same direction or opposite direction? Opposite. Longer or shorter? Longer, so it goes past 0. So what does that tell us about our answer? It's positive, and do we add or subtract the lengths? We subtract. They point in opposite directions, so it's the difference in the lengths. So 19 minus 12 is 7. It's a positive 7. Tell me what to do here. Start with the 32, which is positive. Negative 48. Same or opposite? Shorter or longer? Longer. What's it tell us about our answer? It's on the negative side, and it's the difference between 48 and 32. So let's subtract it, get 16. Yes?
So if you always have your negative number is always bigger than positive, is it always going to be negative one? Or vice
For the
versa?
most part, it is, but I shy away from rules like that because you start memorizing rules like that, then you start looking at subtraction or multiplication, and those same rules don't apply.
But
For addition,
for
yeah.
addition or subtracting,
Well, for addition, if there's one positive and one negative, you subtract. But we'll see some examples where we do still add. So stay with me for a second. So one like this, here's 0. What direction do we go? Negative to the left. That's the negative 274. Then what? Same or opposite direction? Opposite. Longer or shorter? Shorter. So our answer is negative 274 minus 193 is 81. Negative 81. Here's the one I warned you about. Starting at 0, where do we go? Left. Negative 56. Same or opposite? Same. Negative 73. What this is telling us, obviously our answer is negative because both of them go in the negative direction. But this time we take their lengths and we add them. 129, negative 129. They're both negative. They both point in the same direction. So their lengths build on each other. They combine rather than cancel out, subtract.
so why does it?
Okay.
So if you have a negative number,
Yep.
adding a negative number, you're going to get a negative number, but you're adding a negative together.
It's just like this. If you're running a business and you lose $56 one day and you lose $73 the next day, you've lost $129. They're going further into the negative. How about this one? Try that one on your own. Tell me what you get. From 0, we got 218 is positive. Same or opposite? Opposite. Longer or shorter? Longer. So our answer's on the negative side. It is the difference between those, which is 101. So negative 101. Try that one. So negative 93 goes negative. Same or opposite? Same. So it gives us obviously negative 301. We add them together that time. Try this one quick. So from 0, negative 974, same or opposite? Opposite. Longer or shorter? Shorter. So we got negative, we subtract them, 721. Now I realize I kind of pounded on the addition here with the integers, but it's very important because our next step, the subtraction, really deeply depends on an understanding of the addition. If I have something like 8 subtract 3, if I want to draw this out on my number line, the picture I'd probably come up with would look something like this. There's 8, we'll go back 3. We all know that 8 minus 3 is 5, right? But if I'm looking at that picture looks suspiciously like the picture I would draw for 8 plus a negative 3. Because it is. It's exactly the picture I would draw for 8 plus a negative 3. The reason being is that subtraction, as we mentioned before, is not its own operation. Subtraction and addition are the same operation. Just one's going forward and one's going in reverse. Subtraction can be defined in one of two ways. One of the simple ways of defining subtraction is, 8 minus 3 is asking what number plus 3 equals 8. Which is great, but doesn't help us do the subtraction. One of the other alternative definitions of subtraction, of this symbol here to be more specific, is to add the opposite. Now it always works with the number after it. So what does that mean? So what that means is if I have 17 minus 4, subtraction sign works with the 4, the number after it. And it is telling me, instead of subtracting 4, it's telling me to add the opposite of 4. What's the opposite of 4? Negative 4. So 17 minus 4 is the same as 17 plus a negative 4. Either one of them will give us 13 as an answer. Now, when it's positive numbers like 17 and 4, we all know how to do subtraction. So it's easiest just to do the subtraction. But what if it's that? Now it's not quite so clear. People throw out answers like -3 or whatever. It's not. The way this works, as we just saw up here, the subtraction works with the number after it. So nothing happens to the -12. That stays the same. What changes is this becomes add the opposite. Add what? -9. We were subtracting a positive 9, so we're going to add a -9. So now we can look at that and say, okay, here's 0, -12, -9, it's at -21. This one is going to become, does the -14 change? No. It affects the number that comes after it. So subtracting 37 will become adding -37. Good. So here's 0, -14, -37. We end up at -51. Perfect. Now for the one that tends to stump people. That's just what you want to hear, right? Just got to slow down and be careful. The first number never changes. The 17 doesn't. It's the minus here goes with the number that's after it. So instead of subtracting a -5, we change that to adding. What's the opposite of -5? +5. 17 minus a -5 becomes 17 plus 5. Which we don't even need the number line. We know that is 22. Good. So what's this one become? Perfect. 47 plus a positive 118, otherwise known as $165. Perfect. What's going to happen here? Just become a positive 23? No. No, it doesn't. It stays a -23. Nothing ever happens to that first number. It always stays the same. Remember, the subtraction works with the number that comes after it. What's that going to become? Plus, perfect, plus a positive 18. So now I'm going to have to draw a picture again. Here's 0, we got -23. Same or opposite? Opposite, longer, shorter? Shorter. So it's a -5. What do you think? Having a sharp stick in the eye? For now? Okay, well, I'm going to have you guys try some. Try that one first. What'd you get? So we got -7 and a -31. Let's see what we get. -19 doesn't change. This becomes plus a -12. Okay. 0, so -19, -12. Yep. This is -31. Try that one. So, what's this become? 27 plus 32. Of course, that's going to be just 59. Good. So we've got addition and subtraction down, and those are really the toughest ones. Let's look at our multiplication. We had said before, 5 times 3, the definition of multiplication was repeated addition. 5 plus 5 plus 5. And that's why 5 times 3 is 15. With that definition of multiplication, then it's relatively simple to understand -5 times 3. That'll just be -5 plus -5 plus -5. Otherwise known as -15. Five times a -3 might be a little more difficult to understand. This is saying you take 5 and you add it to itself 3 times. This is saying take -5, add it to itself 3 times. How do I take a 5 and add it to itself a -3 times? Well, we don't. What we do is we switch this. 5 times -3 is the same as -3 times 5. When we're just multiplying two numbers, we can switch the order of the numbers. Now that does not work with every operation, of course. It only works with addition and multiplication. Subtraction and division, you can't switch the orders. But if I have it written as -3 times 5, that means I'm taking -3 and adding it to itself 5 times. So I have -3, -3, -3, -3, and -3, which is -15. Perfect. Thinking in terms of my vectors, -3, -3, they all go negative, so it has to stay negative. Here's the stumper. Oops. Now remember, if there's no symbol between the number and the parentheses, it means multiply. So that's -5 times -3. We just said we can't take something and add it to itself -3 times. So we can't take -5 and add it to itself -3 times. We can't even switch the order around because we can't take -3 and add it to itself -5 times. Our definition of multiplication breaks down here. There is no way to multiply those according to the definition of multiplication. Now, some of you are sitting there thinking, wait a second, we were taught to multiply that. What have we been taught that equals? 15. It's been pounded into us. A negative times a negative is positive. Yeah, the question is why? Good question. Well, as I just said, according to our definition of multiplication, we can't do that. And this actually happens a lot in math, where our definition breaks down. Where certain numbers, we can't use the definition of that operation with them. In order to define the answer, then, we look for a pattern. And we define the answer to be whatever continues the pattern. For example, we said that negative 5 times 3 is negative 15. So let's keep going with that. If we keep the negative 5 and let's multiply by 2, what do we get? Negative 10. Negative 5 times 1, negative 5. Now let's see if we can find a pattern here. So if we're starting with negative, that's not what I wanted. So let's erase that and try again. We start with negative 5. If I decrease this number by 1, you can see it 3 down to 2, 2 down to 1. What happens to my answer? It goes up by 5, from negative 15 up to negative 10. Negative 10 up to negative 5. It increases by 5. Let's see if this keeps going. So negative 5 times 0 has to be 0. Okay, so this went down by 1. Did this go up by 5? Sure did. So that pattern seems to work. So now we're just going to assume, now that we've found a pattern, we're just going to assume that it continues. So that means negative 5 times negative 1 has to be, well, this has to go up by 5, has to be positive 5. Negative 5 times negative 2, well, this has to go up by 5, has to be positive 10. Negative 5 times negative 3, this has to go up by 5, has to be positive 15. When we define that a negative times a negative equals a positive, the only reason for that is because it fits the pattern. So let's say I have negative 7 times negative 5. What do I get? Positive 35. Negative 8 times 3, 24. Negative 24. 9 times 6, 54. Yeah, 3 of these ones. 4 times a negative 8, negative 32. Good. Okay, I'm going to give you guys a few to try on your own here, quick. Try those 4. So the only thing different about these from any other multiplication we do is we have to decide what sign it is, whether it's positive or negative. So first we're going to do that. For the first one, positive or negative? Negative. And now it's just 7 times 6, which is 42. So negative 42. Positive or negative? Positive. 5 times 9? 45. So that's just a positive 45, or 45. Positive or negative? Negative 18. Good. So you can see the multiplication of the numbers is the same. We just have to decide whether it's positive or negative. Positive or negative? Negative. And 32. Perfect. So our little pattern, of course, a positive times a positive, that's always positive. Positive times a negative is negative. Negative times a positive is negative. Negative times a negative is positive. So the key is right here. If there's one positive and one negative, no matter what order they're in, they will multiply to make a negative. Let's look at division. To deal with division, we look at the fact that division is, again, a byproduct of multiplication. 16 divided by 2 equals 8 is defined because, you work backwards, 8 times 2 equals 16. So if I ask you 27 divided by 9 equals what? That's asking what number times 9 equals 27. 3, of course, yeah. So when we look at our integers, it's the same way. If I have a negative 32 divided by 4, what that's asking me is what number times 4 equals a negative 32. Now here, this is negative. Since the 4 is positive, this one must be negative. And of course, it's going to be negative 8. So 32 divided by 4 is 8, but because of the 32 being negative, it has to be a negative 8. So you can see, just like multiplication, the division doesn't change. We just have to decide whether it's positive or negative. 42 divided by a negative 7, well, same thing. This is blank times a negative 7 equals 42. Well, if this is positive, if this is negative, this one must also be negative, because a negative times a negative gives us a positive. And of course, it'll be a negative 6. 42 divided by 7 is 6. If we have negative 24 divided by a negative 8, same thing. Blank times a negative 8 equals negative 24. Well, this is negative and this is negative, so we have to multiply it by a positive. So this is going to be a positive 3. So it's the same thing. Just like with multiplication here, we see that if we have one of each, one positive and one negative, our answer comes out to be negative. If they're both negative, the answer comes out to be positive. Well, enough of strictly working with negatives. We're going to look at then a new operation. And that operation is exponents. And we're actually only going to look at one portion of the exponents, because exponents include what we call radicals, or roots, and powers. Powers are the portion that we're going to be looking at today. What does that mean? 7 squared, or 7 to the power of 2. What does it mean? 7 times 7, good. Or we could calculate it out to be 49. All right. What's that mean? We got 8 to the 3rd power, or 3/8 multiplied together. Otherwise known as 512. 8 cubed is another way you could pronounce it, yes. Yeah, squared and cubed for 2 and 3 for the powers. Of course, this would be pronounced 5 to the power of 4, or 5 to the 4th. What's it mean? Yeah, 4 5s being multiplied together, or 625. Now, some of you are sitting there looking at, well, where did the 512 and the 625 come from? It's not magic. I swear. More importantly, how can I calculate it myself? Well, you could do by hand. 8 times 8 is 64, and times 8 is 512, and so on, but I'm guessing you don't want to. So if you look on your calculators, your calculator will have one of a couple of different buttons. The most common button looks like this. It is called the Caret Key, because it looks like an upside down carrot pointing up. You may also, depending on if you have a one-line display or Casio or Sharp, some of those have a Y to the X or an X to the Y key that looks like that. Or some of them have one that looks like this. It has like just gray boxes that look like that look like powers. All of those buttons work exactly the same way. If I want to enter 3 to the power of 5, I do 3, press whatever key that is, enter the 5, and hit equals, and it better tell you 243. Yes? No? No? So type in the 3. And on yours, I think it's the... Let me take a peek quick. On yours, it's the Caret Key right there. Okay. Nope, that's only for power key. That's
Okay, I did that too.
Some of you actually have an X squared key that only works for the power of 2.
Oh.
So you have to use the caret for any other power.
Okay.
Did that come up to 243 now?
Yeah.
Okay. Well, I'll race you on this one. Ready? Did you get it?
How did you know?
I've done these a few times before. Math is about patterns. Once you start to see the patterns, the calculations come really easy. It just takes a long... You got to remember, I've done math pretty much every day of my life for like 17 or 18 years now. I know I'm not in a padded room yet, but I'm probably pretty close.
Is there another way to figure?
There are other ways to figure out what comes into those patterns. Once you see the patterns, there's ways to make the calculations a lot quicker. And unfortunately, you can't just sit there and describe the patterns. You have to start to see them. But that's why we talked about the count and the name last class. That's why I describe things that way, is that when you see things like that, the patterns start to become more apparent. This one now, -7 squared. Try that one on your calculator and see what you come up with. First of all, how do you enter the negative? Very good. A lot of you down by your equal sign will have a button that looks like this. Has a minus in parentheses, that's your negative key. Others might have a key that looks like this. That's your change sign. If you have this key, you type it in just like that, -7, and then go from there. This key here, you'd have to type in the 7 first, then you hit that key to make it negative. Now, what did it tell you for an answer?
-49.
It said -49, but let's think about that. This means -7 times -7. A negative times a negative has to be a positive. Your calculator didn't screw up. We just all entered it wrong. Notice how I wrote it here? In parentheses. If you just do -7 and then squared on your calculator is applying the squared to the 7 and then putting the negative in front of it. So you do actually have to use parentheses when you enter this. You have to do the open parentheses, -7, close the parentheses, and then to the power of 2. 49, you got it. Any number squared must be positive because a positive times a positive is a positive. But a negative times a negative is also positive. So if I have -21 squared, is it going to be positive or negative? Positive. Any number squared must be positive. So when you take a negative number to a power, you must put it in parentheses to make sure your calculator does it right. It's going to be positive. How about negative 2 to the power of 5? Is that going to be positive or negative? Careful. That's saying 5 negative 2's, right? These two multiply to be positive 4, right? This one multiplies with that one to become a negative 8. Multiplies with that one, now it's back to positive 16. Times the negative 2 is going to be negative 32. Why is that one negative when this one was always positive? It's not a 2, it's power of 5, right? It's a different power. If it's a power of 2 or if it's squared, it'll always be positive because it's just 2 negatives. Here, though, there was 5 negatives. There was that extra one to make it. Oh, there it is. Somebody got it. I thought I was going to have to do several more examples to get there, but good catch. If that power is odd, there's going to be an odd number of 2's. Notice the negatives can pair up and cancel out to be positive. But if that's an odd power, there's one left over to make my answer negative. So if I have negative 5 to the power of 7, that answer is going to be negative. In fact, it'll be negative, what, 78,125, something like that? Okay, it is about time for us to take a break, so let's do that. It is, we'll call it 4:23 right now, so we'll come back at 4:33.